Okay, we have discussed about different formulations using the isotropic assumption. So he will discuss a bit about bone orthotropy, but that is sort of an extension of bone mechanics, just to say a little bit more in-depth knowledge about bone characterization. Bone anisotropy, bone orthotropy, things like that, how things have evolved. Very recently, actually, we have come up with a orthotropic bone remodeling algorithm that has been published in this biomechanics and modeling in mechanobiology. But generally speaking, he will be brief. It is definitely a little bit advanced level, but that is, we will try to be as friendly as possible to explain things in a more simple way. But what I felt that the students should be exposed to the fact that most of the simulations are done basically based on isotropic assumption, which is not actually the reality. There may be subtle differences in results, but we have to recognize that more isotropic. Okay? Did you get the point? Hello?
Yes, sir. Yes, sir. We got it.
Yes, sir.
So, if you face an interview board and say somebody asks you how do you characterize bone in form of an engineering material, is it isotropic, anisotropic, orthotropic, transversely isotropic? So that at least. So how bone material properties? Because as you know that there is trabecular orientation. And so bone grows according to the loading it receives. The trabeculae, they are oriented along the direction of principal stress, direction of the principal stress. These sort of facts, which are nothing, too difficult to understand. With your background, it should not be too difficult. But what people have done, why people have done, for practical reasons, heterogeneous isotropic modeling bone as heterogeneous isotropic has been found to be quite practical. That those sort of things maybe he will be discussed. But anyway, next week I'm actually going off to Bangalore for a very emergency situation of my mother. So I'll be traveling tonight. Tomorrow, SEBI will be taking the class on the bone orthotropy. Friday is a holiday, so you can enjoy your long weekend. But I am returning from Bangalore on Wednesday, so I cannot do a class on Wednesday. I'll be in flight Thursday, and by Friday. Thursday, I will discuss a little bit about certain experimental validation. That is for your knowledge. Thursday, Friday, I have kept for complete doubt clearing wrap up. Is that okay? So next Wednesday, no class. You can of course, I can request SEBI if you want a doubt clearing class with SEBI, you can do that. Go ahead, that's no problem. But I will take a class on Thursday, on 8th, and if necessary, 9th. For any doubt clearing session, anything. 12th, we are having the exam at 6:30. Is that clear? So this is basically the plan. So tomorrow SEBI will be taking the class. Okay, so quickly I will move to a very brief lecture on the implants, so as to say. We have discussed earlier So I will go to share screen. Can you see the screen? Hello?
Yes, sir.
Hello?
Yes, sir.
Can you see the screen presentation?
Yes, sir.
Okay.
Yes, sir.
So I will just meeting option. Good. Okay, so this lecture will be on orthopedic implants and biomaterials. Okay, so more the practical aspects of implants. So as you know, that orthopedic implants are artificial devices. Basically, these are medical devices, and they are used basically to replace bone, joints, as well as for fracture fixation. So primary function is to offer pain relief and to restore normal movements. Okay, so artificial device of any sort that can actually replace bone and joints. But remember, apart from joint replacement, the very elementary level implants are plates and screws. Okay, that is used for fracture fixation. Okay, here you can see in the picture an example of, well, of course, you have seen earlier knee implants. I have shown you hip implants, but on the right and on the below are, on the right is a spinal implant. So inside the vertebra, there are also certain components that together with the rods and screws, they are fixing a degenerated spine. Okay. This is plates and screw system. You can see here very clearly there is a fracture, as I am pointing with my pointer, and there are plates with screws which are used for basic fracture. Okay. So implants basically starts very elementary level is plates and screws, then joint replacement, spinal implants, in general. The implants are commonly made from, okay, they are commonly made from historically metallic alloys. Still metallic alloys are very much there. There is of course polymers and polymer composites, okay, and ceramics. There are not many variety of metallic alloys as biomaterial, because why that is so, we will discuss that little later, because there are certain major requirements of biocompatibility. Okay? Biocompatibility is a major requirement of a successful biomaterial regarding application in orthopedic implants. I think we had discussed about this, but generally speaking, we can classify fixation into two types. Okay? We have the cemented fixation, the age-old cemented fixation, which is still used in certain patients. So depending on the patient condition, actually we nowadays, a surgeon chooses a particular implant type. Okay? Will it be a cemented fixation or uncemented fixation? Now, when we call about cement, then of course the material that is used to fix an implant to the bone is bone cement. And it is actually a polymer. Okay, its short form is PMMA, and the full form is called polymethyl methacrylate. Okay, polymethyl methacrylate. That is or PMMA. Okay. The advantage of this type of fixation is very good initial fixation. Within 15 to 20 minutes, maximum half an hour, the cement is cured and the implant is fixed with the bone. However, there are many problems later on associated with cement or the cemented fixation. Now, bone cement, similar to building material cement, it has a very low tensile strength. Okay, around 20 MPa. Okay, but this is the static strength. If you go towards fatigue, it will come down to 7 to 8 MPa, say 500,000 cycles. So that is pretty low. Okay. So cement may actually crack at a very low tensile stress generated within the cement mantle. Okay. It's highly prone to cracking. Now, the moment it cracks, it can disintegrate the interfaces it shares with bone and implant. There also, if you apply Hoffman's failure criteria, you may notice that there would be debonding at these interfaces as well due to the low value of tensile strength. Now, the cemented fixation actually is undertaken. I'll briefly discuss the procedure. The bone cement comes in the form of a powder, like flour. Okay, you know, you roti jo banata hai or puri banata hai. So we use sort of, so it comes in the form of powder, and there is a monomer, a liquid that mixes together. The moment you mix the two, there is, and you mix it very hard. They use it the vacuum mixing also, so that the mixing is very good quality. It will become a semi-solid type of material. Okay, so it will very fast try to solidify, but it will be semi-solid like a dough. Okay, now during this period, when it is actually a semi-solid, it was powder form, then we put the monomer and then we mix it very hard. There is a huge thermal reaction. There is an exothermic reaction. And when you have to, as a surgeon, you have to mix it fast. And when it is still in the form of dough, you have to push it in. You have to push it in the reed hole, and then you place the implant in the desired position, and then you let it solidify. So what happens is that there is a case of thermal injury being caused at the bone interface, because the cement temperature in the bone cement mantle that is pushed in is maybe about 80 degrees centigrade, 70 to 80 degrees centigrade. So that might cause thermal injury. Okay. Now, apart from that, as you can see, osteolysis caused by cement particles. Now, the way the cement stays inside the implanted bone structure. Now, as I told you, due to its inherent failure, maybe due to low tensile strength, maybe due to interface debonding, with continuous use, cement particles, very small size cement particles would be generated. Okay, and those cement particles actually can react with bone cells and cause osteolysis. Osteolysis is a phenomenon by which we can say bone loss happens. The end outcome is bone loss. So it can react with bone cells and it can cause osteolysis. Okay. Necrosis, as I told you earlier, is a phenomenon by we can say low blood supply. So cement can, because of various types of events, maybe due to also thermal injury, it might lead to some sort of low blood supply in the bone cells adhering to the cements. Okay? So that would form necrosis. So, however, one big advantage of this procedure is that it can give you almost immediate fixation, even before the whole surgery is complete. So, in many patients with very poor bone quality, highly degenerated bone, osteoporotic bone, surgeons have been still preferring cemented fixation. However, the much better alternative that has evolved over the last decade is uncemented fixation. Okay? So it is another type of fixation, but not using cement. So there must be a biological fixation between the implant and the bone. And that's called uncemented or cementless. So in this type of implant, you can see, if you look into the inset picture, that there is porous coating already on the bone, on the implant, and the bone actually grows inside into the pores of this implant to form a permanent bond. Okay. So the more the bone ingrowth, the better will be the mechanical interlocking between the porous coating and the bone. Therefore, yielding a very durable interface or durable fixation between the implant and the host bone. Okay? So in the long run, this biological fixation is certainly better than the other variety, which is a cemented fixation. So with time, actually, these disadvantages of the cemented fixation, becomes more and more troublesome for the survival or the outcome of the reconstructive surgery. But once you have an initial fixation, once you have some amount of bone ingrowth, and that can offer you primary fixation. With time, this type of fixation or interface is a better alternative than the cemented variety. Okay. So the advantages are higher clinical success rate in young and active patients, because biological fixation offers basically long-term fixation. Okay, the biological fixation of the implants offer long-term fixation. So for young and active patients, particularly, this is preferred because bone can grow very easily at a younger age as compared to an old patient. So the more the bone ingrowth, the better is the osseointegration of the implant with the bone, thereby offering you more long-term fixation. Okay. But initially, you have to apply a press fit. You need to apply press fit to hold the implant inside the bone. So the press fit is required for initial stability or initial fixation. And the most importantly, the whole fixation technique is dependent on adequate bone ingrowth that can offer primary fixation or initial fixation. Okay? But just to show you some examples of, say, hip replacement. So I told you earlier, this is typically a hip implant. So the femoral component, as you can see, and you can see here, this is an uncemented variety. You have a porous coated surface towards the proximal side of the implant where bone can grow. So this is the head, this is the neck, and this is the body of the implant. This is a total hip replacement or total hip arthroplasty. The other thing, the socket, is the acetabular socket. As you can see, it is also porous coating in the undersurface of the implant where bone can grow inside. So both the system, the acetabular component and the femoral component, are uncemented, as is seen from the picture. Okay. So this is total hip replacement. Just see that from the neck, pay attention to the figure on the left. From just below the neck, the whole bony part up to the femur head, they have been resected and thrown away. Okay, and the implant is inserted, as you can see here. Okay. But in case of resurfacing, we actually machine only a part of the femur head. You can see here the neck is still there, and of course a part of the head is still there. And you insert this resurfacing implant with a stem, containing a stem inside the bone. But the acetabular component actually is almost the same. Okay. To be honest, the acetabular replacement, or acetabular prosthesis, acetabular component as you call it, is in both cases surface replacement. Okay. The design can vary, but it is essentially a surface replacement, the acetabular component. Only the femur, if you consider the femur, the surface replacement of femur grossly differs from the total replacement because very minimum bone is removed in case of the femur surface replacement, whereas the proximal part of the femur is resected and thrown away in case of total hip replacement. Now, varieties of design of uncemented femoral implants have evolved in the market over the years. And you can see that, orientation of the implant is completely different. There are different shapes, different sizes. We should talk about shapes if we talk about designs. So, over years, many things have been reported, many problems, and accordingly, new designs have evolved in the market. The failure mechanisms, as I told you, the most common failure mechanism I have already discussed earlier in the class is based on the mechanical environment. So you can have excessive stresses within the implant itself, also at the interfaces leading to implant bone interface to body. You can have, micro motions between implant and bone. In case of cement, it would be cement and bone, or implant and cement, two interfaces. So you can have relative displacements if the implant is not fixed initially. So that may affect the primary fixation. Okay. The second part, the second failure mechanism, is connected with wear particle debris. I have told you a little bit about the wear and abrasion of cement particles, but wear and abrasion of not only cement, it can actually have also, it can be at the interface of cement bone, cement implant, anywhere. It can be abrasive materials coming out of the interface. And these very small particles are highly reactive. The material itself, bone cement, is a bioinert material. It is highly biocompatible polymer. But remember, small particles of the inherent, these materials, implant materials or the supportive materials, they can be reacting with bone cells, blood cells, bone, blood, all tissues, and they can have actually very bad effects in the long run. Okay. The same thing is when two components of the implant system are articulating, say a femoral head with a scapular component, spherical scapular component, and with continuous use, you can have high volumetric wear rate. Okay, the more the volumetric wear rate, the more will be the wear particle debris that is created within the reconstructed joint. And with a lot of wear particle debris, it can actually react with bone cells and any body cells, bone, blood, other tissues as well. So this is a big area where a lot of research goes on, biotribology. Okay, so the tribological aspects of the implant material is of important consequences. Now, if we consider historically the Charnley prosthesis, as you all know, that Sir John Charnley was a pioneering man who had discovered this hip replacement. Okay, and he had a stainless steel femoral implant and a high density polyethylene acetabular component. So with that, it was the first gold standard of hip replacement. Okay, he was in fact from Leeds, and I have, since I was associated with DePuy Johnson and Johnson, there is a lot of excitement still remaining in Leeds about this, about the evolution of hip prosthesis, which is still considered as the gold standard of joint replacement. Now, what has happened over years is that polymer, the acetabular component, which is made of polymer, that generated a lot of wear debris. And that the wear debris generated from the polymer material actually reacted with bone. And eventually, it led to failure of the implant bone system. Now that was realized after 10 years, 10 to 15 years. Thereafter, there was, suggestions of metal to metal bearing surface. So metal femoral component and metallic acetabular component. Now with follow-up, it was found that metallic ions were released due to this articulation. And these metallic ions were actually reacting at the ionic level with the living tissue, bone, blood, everything, and causing also some negative effects in the whole system. Now, just upon realization of the metallic ion release, there came the suggestion of ceramic to metal bearing surface or polymer composites like PEEK, PBT. Okay, so PEEK, I will discuss later when I'm in PEEK, the biomaterials, but PEEK, the polyethyl ether ketone, has evolved as one of the most successful, as of now, of course, So it is time related. What is successful today can be prove failure after 10 years. Okay. So as of now, peak polyether ether ketone, it has evolved as a very good wear resistance polymer composite having an E modulus close to cortical bond. Okay, so that serves a lot of purpose. Now, poor osseointegration, as I told you, long-term stability of uncemented processes depends on the biological fixation or on osseointegration of the implant through bone ingrowth within the outer porous coated layer. We have discussed enough about stress shielding or strain shielding and its effect on bone remodeling. So any adverse bone remodeling will actually lead to bone loss due to changing mechanical environment. Now, there is also other things, separately a wear, a destructive wear is mentioned here. It of course comes within the particulate reaction failure mechanisms. The continuous fretting between components of modular prosthesis and abrasion of bearing surface generates wear particles and might lead to scenario where mechanical integrity of the component is no longer maintained. Now you might have observed, if I show you some implants, maybe on here, maybe here, you can see that this is the body of the femoral implant. 1, 2, 3, 4. But a head needs to be put inside. The femoral head is missing here. So this is, a modular type of design. You have a head actually. It may be a ceramic head. It may be a metallic head, spherical. It needs to be pushed in. Okay. So fretting or wear between parts of the prosthesis, that can also generate wear particle debris. Okay. So which can be highly reactive to the living tissue. Now, apart from all this, when you insert an implant, due to the design of the implant, maybe long stem, the tip of the stem might be impinging on the cortical bone, say for a hip implant. And that impingement can also cause fracture of the femur. Okay, so there may be failure of cancellous bone, there may be failure of the cortical bone due to insertion of the implants. Now, over the years, it has been implant design analysis is a continuous process. And I hope the students have got a good exposure of the failure mechanisms and the problems, how things are designed as well. Now, the idea of developing porous implant originated from the failure mechanisms, considering the failure mechanisms of solid implant. Okay. Now, anything solid, as you can see, the hip implant, means it will be very rigid. You are pushing inside something which is very rigid. And hardly there is any failure of the implant itself ever. So you might not need actually that amount of rigidity. What happens if you have more rigidity in the implant, more emodulus, then actually it causes stress shielding, leading to adverse bone. You also need to actually have good fixation, biological fixation, because nowadays more and more implants are uncemented. So you can see the body. Now what has been done is people have considered making part of the body of the implant with porous material. It may have a solid part, less solid part, and more porous part. Lattice structured implant. So you can see also here spinal implants. So the beauty of this system is that bone can grow very easily inside and form a very strong bond to hold the implant in position. Okay. So porous implants facilitate bone ingrowth into the interconnected bones, thereby enhancing long-term stability and reducing stress shielding. Now, for this sort of structure, a porous implant, the E modulus will be different from a solid implant. So you can calculate it using homogenization principle, because the matrix that will be formed is out of if bone grows inside the pores, so bone and implant together would form a matrix. The properties can be adjusted to the use of appropriate core structure and morphology. Okay? So you can design a favorable porous implant to facilitate more bone ingrowth, less stress shielding. Now let us come to biomaterials. So biomaterial is, of course, a substance that is engineered to interact with biological system for medical purposes, to solve medical problems. Now, the primary requirement is biocompatibility. So that is it must be bio-inert. It should not react body, bone cells, blood cells, marrow, anything. And it should not be non-toxic, should not have any toxic effect. So the ability of a material to perform with an appropriate host response in a specific application. So biocompatibility is the most important requirement of a biomaterial. Adequate mechanical strength in static and fatigue load tension, compression, shear is required. Sufficient stiffness and hardness, giving rise to more rigidity. So it cannot be very flexible type. It has to be something, a moderately rigid implant. It should have ductility property. Resistance to corrosion in presence of body fluids, singly or in combination with other materials. It must be a wear-resistant material with regard to articulating parts, and it should have a longevity both biochemically and dimensionally. Okay. Metallic alloys have passed the test of biocompatibility. Okay. Started with stainless steel, surgical grade, AISI 316L, which is around 200 GPa. Titanium alloy with half the density of stainless steel or steel in general. It is almost half the density. Okay. It is lightweight material, but its strength is almost similar. And you can see the E modulus is also about half. That means less stress shielding effect, less rigid. But it is a soft material, remember. It can be used for a body, but when it comes towards the articulating zone, you cannot use, say, a femur head. It cannot be made out of titanium alloy because it requires a minimum amount of hardness because in the articulating zone. So cobalt chrome molybdenum alloy is a very frequently used implant material which is hard and used in many applications for implants. Tantalum is another material that is evolving as a metallic alloy. for different applications. Okay. So for metallic alloys, metallic implants are the primary biomaterial used for joint replacement. So be it hip replacement, be it knee replacement, still metallic alloys form. There is a big contribution of the metallic alloys in the implants. Basically due to high strength, high facet toughness, corrosion resistance, and biocompatibility. The disadvantages are basically high elastic modulus. You have seen that it may cause stress shielding and adverse bone remodeling. And the toxic effects caused by metal ion release when two metallic components are actually articulated. Okay, that is a very recent problem that has been observed with metallic implants. Polymers, ultra high molecular weight polyethylene. As I told you, on the top, it has found applications in tibial implant, knee prosthesis. It has found application in acetabular component. As you can see here, the pictures, both one is a tibial component, only one part, modular part, which is articulating, and you can see the acetabular component as well. Okay, PMMA I have discussed is basically the bone cement, that is also a polymer. It's basically lightweight and elastic modulus is almost similar to bone. And you can actually synthesize polymers according to your requirements. Okay. You can have polymers, highly cross-linked polymers that can reduce wear rate, volumetric wear rate. But generally, and a very important disadvantage of polymers is poor wear properties. It has high volumetric wear rate, and it is a less probable candidate for polymer with bone interface is always a big problem. Okay, you cannot generate some porous coating on that, so that is, and it's always loose, and it can, with generation of wear particle debris, it can react with bone very easily. As I was telling you, polymer composites like PBT and PEEK has evolved. PBT found application in Cambridge cup. In Meech cup, we have explained you, PEEK has come up very fast as a favorable polymer composite biomaterial in implants. PEEK found application in spinal implants, spinal spacing, within the lumbar spine with spacers, and it has found application in that. Of course, you have advantages of high mechanical strength, high fatigue resistance, but very low volumetric wear rate. Modulus of elasticity is close to cortical bone, and that eliminates somewhat the stress shielding. And they can transmit X-rays, CT or MRI scans without artifacts, so it is easier to monitor bone growth and the healing process. Okay. A disadvantage is PEEK has a lower surface energy due to its relatively hydrophobic surface, and it somewhat limits cell adhesion. Okay, so if there is no adhesion between the cell, bone cell, and the PEEK material, that means the bone ingrowth will be hindered in that surface. Ceramics, as I was telling you, aluminous ceramics finds a lot of application in the form of acetabular component. You can see ceramic to ceramic bearing surface is also available. So you have a femur head with ceramic. You have a liner with ceramic. So these are ceramic to ceramic, highly polished ceramic to ceramic articulation. And this acetabular liner goes inside a metallic shell. And you can see the undersurface of the metallic shell has a porous coating. Okay. So this liner along with the metallic shell actually forms the acetabular prosthesis. And this part, ceramic femoral head, actually goes inside a femoral stem, as you can see here, and it forms the femoral implant. So it has very good, ceramic has certain excellent properties like no corrosion over time, bio-inert and stable, and it is very hard material. But you see, the elastic modulus is almost 1.5 times that of steel itself, or cobalt chromium molybdenum alloy. So it's a highly rigid material, and there is some still concerns about the brittle properties, which can result in fracture of the component. So that's it. A general overview of implant and biomaterials. Questions, please. Yeah, you can ask questions if you like. But if you read the slides, you can easily understand it. And you can also refer to your way of searching things if it interests you. Hello?
Yes, sir.
Could you follow everything? Shivanshu?
Yes, sir. Yes, sir.
It should be easily understandable because we have discussed about all these things in different parts, actually in detail.
Yes, sir.
Now you have a holistic knowledge about the whole subject, so it should not be a problem to understand what is the requirement, design requirement of a good implant. Isn't it?
Yes, sir. Sir, in older people and younger people, is there any difference of recommendation of these implants?
Yes. Good question. The first requirement, first thing that you have to keep in mind as a surgeon is the younger patients are very active patients. Okay, the young means in 40s, maybe 50s up to 55, 58, because the patient is leading a normal, professional life that you expect, and he's busy, he's jumping around here and there. So that is what is called active patient. Okay. So you have to offer him a solution in a way you cannot let a pain to go on. He should have an implant which can serve him or her for about 20 years without any problem. Isn't it? So if consider a patient of 40 years old, so he has still a working life of 20 years. Later on, he can actually replace certain parts, but basically the implant needs to be seated very securely within the bone. But for an old patient, the scenario is completely different. You may, when you look into the X-rays or you open up, you see that bone has degraded to a great extent. And an old patient, you don't expect him to run around, lead a very professional life, a corporate style life, or a very busy life altogether. So what the patient needs is that he or she should be able to do the normal daily activities, maybe even go to a golf club and play golf or drive Insert our car and climb stairs, do normal daily activities, sitting down on a chair or a bed, getting up, do normal activities. But you don't expect an old patient to run around like a young patient at 40, 45 with you. So accordingly, the implant system chosen for the two group of patients of different age is different. So young and active patients, a surgeon in 100% cases will go for unsymmetric fixation. I know one of my friend's mother was operated due to last year two happened. My classmate's mother, they were operated with hip prosthesis because they had a fall, and immediately what happens is the femur neck fracture. Now at this age, you cannot, in 76, between 75 plus to 85, in this age group, you cannot put plates and screws to and let the neck of the femur heal, because they will hardly be successful. It cannot be successful. Bone growth at that age is almost impossible in nature, so that it can sustain a heavy load like that. So it has to grow to that extent. So what the doctors do, even if there is a neck fracture, they remove the proximal part and they insert a prosthesis. And they have used uncemented prosthesis. Very, very successful. And I was sort of quite excited to see that those things happen, because for both the cases, I was a sort of advisor. And one of the surgeons I knew very well, he's a good friend of mine, works in Fortis Hospital now, but he was in England where we worked together at one point of time. So uncemented variety is actually the way forward, because the biological fixation is much more durable than a cemented fixation. But still there are many cases where the surgeon is a bit reluctant or is a little bit worried whether or not there would be enough bone ingrowth to hold the prosthesis in place. Okay. And if it doesn't happen, then it is a dangerous situation, because the implant is almost mobile from day one. Okay, and then that is another big problem, threatening the total reconstruction procedure, because you need to fix the implant and hold it in position. Otherwise, it's completely loose. You see mechanical loosening from day one, and that's failure of the system. Okay, did it answer my question?
Yes, sir.
So there are a lot of requirements, very fine observations. A surgeon has to decide many things, keeping all these failure mechanisms in mind. And the patient, bone condition, the age, what sort of lifestyle he or she leads, those things contribute a lot towards this decision. But yes, very grossly, you cannot expect an old patient to do gymnastics or play badminton or do some sporting activity, do you? You expect him or her to do some fast walking. maybe maximum a bit of jogging, isn't it?
Yes.
That's a big difference. That's a big difference. So it's quite common for a person, of the age 45, 50 to play lawn tennis or badminton, isn't it? Have you heard of Milkha Singh?
Yes.
Milkha Singh was operated. Milkha Singh, Bishan Singh Bedi, the cricketer, this is athlete Milkha Singh. I have met him in a function in Delhi, and he was operated by the same surgeon who operated my mother in Delhi. Okay. But imagine Milkha Singh and also Bishan Singh Bedi. So Bishan Singh Bedi was always a fitness freak, although he had a big belly. He was off spinner, but he was, of course, a fitness freak. But they are all fitness freak people. And you see, they have been replaced with knee. But their knee replacements were more of the mobile type of, it's more flexible prosthesis. There are certain designs which offer you large range of motion as compared to some normal implants. Highly mobile prosthesis. Mobile in the sense means that it offers you more mobility, more range of motion, because they are still doing some sporting activity. Okay? But remember, always more mobility will actually implicitly mean less stability. You get my point? So you need to be very careful about it. Okay? I have to end the class now. We can discuss more next Thursday and Friday. We can have a holistic, very friendly discussion about this. Okay?
Yes, sir.
So I'll upload these slides so that you can go through it. And then I take it from there. If you have still questions, you can post it. I will answer them. I'll carry my laptop to Bangalore. Okay? Thank you all.
Thank you, sir.
Thank you, sir.